Hi, everyone. I'm an applied researcher at eBay, which is a large e-commerce company. Let's talk about, sorry, 1 second. So this is the outline of the presentation that I'll be giving today. So I'm going to talk about the customer problem that we're interested in, the resolution to that customer problem, which we call visual search, and then a small research topic that I think might be of interest to this audience. So let's start off by talking about the current customer experience at eBay and how we seek to improve it. So in terms of scale, eBay operates at a massive global level. We operate in 190 countries, and as of Q2, we had 138 million buyers. So there are a lot of people that will be affected by any particular change that we make to the search system or the search service. Well, what are people actually buying on eBay? So these are our major categories. They're watches, sneakers, trading cards, and refurbished products. I personally have spent time working on sneakers and trading cards, though not so much on the other two. Today, we'll be focused on categories that are less popular in the US but are bigger in Europe, namely Germany, and those are both furniture and home decor. Pretty intuitive what the content of each of those is. So let's talk about what the current customer experience looks like. So to start off, maybe just let everybody have a moment to come into the room. Okay, so has anybody here used eBay before? Has anybody bought anything on eBay? Oh, wow, okay, that was actually quite a bit more than I expected, so that's great. I guess the Armenian market is probably saturated then. For the rest of you, after this talk, you'll all be running to use eBay. Okay, so like you saw, the text experience is mostly search-driven. You submit a query, just like you would on Amazon or anywhere else that is text, and you get as a response some combination of an image, a score, a title, a price, that kind of thing. Each of these results is called a listing, and you can think of a listing as sort of the most atomic unit at eBay. So sellers are allowed to even post multiple listings themselves that describe the same product. So we can see here, for instance, here are two different listings that are the same product. So just to discriminate, like it is not the case that a listing is the same as a product. Products comprise many separate listings. So we'll see more about the anatomy of a listing later. It's worth noting that there are other ways that you can browse eBay, but this is by far the most popular. I work in search, so I work on this one. This is what we'll be talking about for the talk. Okay, so that's the background. Let's move on to the exact problem we're hoping to resolve. So like I said before, the current search experience is text-based. So we can imagine this as the kind of typical user experience process. This is me, and I'm interested in buying a nice Killam pillow for my couch. Okay, so I go ahead and I do a search for Killam pillow, and I get some results. I look through the results, and I find that they're not really to my liking. In particular, in contrast with the image I had in my head, these are insufficiently orange. Okay, so I go ahead and I just add that to my search. Search for an orange Killam pillow, and again, we get some results. There we go. This time they're maybe a bit more orange, but nothing is quite to my liking. And as I scroll through, I identify a particular vocabulary word that hadn't occurred to me to use, and that vocabulary word is throw. There are a lot of throw pillows in there. So finally, I come to my last one, which is I do an orange throw Killam pillow, and I find some results, and I find one that looks pretty good to me. So this is the typical experience for our users. They go through many iterations, and they learn from their previous search results, and they try to adapt their language in a way where they can better communicate with the search engine. Okay, so let's suppose now a slightly different but related scenario. So in this scenario, the user has managed to find an approximation of the kind of listings that they want, but we want to offer them an experience that relies less on the text. So what are the desirable qualities of this kind of search? Well, we don't want to show our users listings that are the same from the same item over and over again, like describing the same product. We do want to show them listings we think that they'll be interested in, and we want the similarity to be based on the image itself. We'll talk a bit more about that later. So in our example, the user has managed to find an approximation of the listing that they want, but it's not quite right. So we present them with this see visually similar items link. You probably can't quite read it, even with my glasses, I can't due to the focus, but it says see visually similar items. So they click that, and this image gets sent to some kind of search service, and a list of results is returned. In this list of results, there are a lot of pillows that look pretty similar to that one and maybe a little different from the other pillows that appeared in the initial search. So, and looking in here in particular, we see my dream pillow, my ideal Killam pillow that I've been searching for all this time. Okay, so we call this experience visual search. So the main thrust of this talk is about how we at eBay got visual search off the ground in a pretty tight timeline. Okay, let's get into it. So how are we going to do it? How are we going to do it? So let's imagine a two-step process. First, we're going to create image embeddings somehow. And if the embedding that we create is inferred from just the image, truly being an image embedding, then that means that users cannot easily hack the search system by changing the vocabulary words that they enter into the textual component of their listings, which is a pretty typical problem for us at eBay and probably anybody that operates a text-based search system. So at query time, users will select an image, which will be submitted to the search service and compared to the other listings. And then the comparison will be based on like a KNN search. Some results will be returned. They can be sorted either by the KNN similarity or by some other kind of ranking. I won't get into that, but that is another important component of this process. So instead, we're just going to focus on literally the image embedding production part of this, which is where the modeling is and most of the machine learning is. So what do we want from these embeddings? Well, the simple quality that we desire is that similar images are mapped to nearby points. It's a little bit vague, but that is the target. So that leaves a number of open questions. How should we train such a model? And do we already have data for it? So in this section, I'm going to talk about some of the data that's available to us at eBay. There's a lot of other data that is not necessarily public, but these are all exposed to you. If you go on eBay, you can see all of this contained within the listings. Okay, so, and we'll go through the different options and see sort of a pro-con list for why we would use each one for training this type of model. Okay, so the first is category data. So the name is pretty intuitive. The categories at eBay actually form a hierarchical tree structure, but the categories that I'm interested in are the sort of lowest lying ones on that tree, the leaves, and they're moderately descriptive. They're things like men's athletic shoes or dining sets, but they don't actually get any more refined than that. So you can imagine training a model wherein it takes in an image and tries to predict the category to which it belongs. And that would work. That would get you, image embeddings that you could then use for a search system. But thinking about the limitations there, well, men's athletic shoes isn't very specific, right? It's a pretty broad and I would say non-descriptive collection. So men's athletic shoes, in fact, drives like a huge fraction of eBay's sales because of the popularity of Nike and things like that. So this is, in our minds, nondescript. Okay, the second one is called aspects. So aspects are key value pairs that are appended to every listing at eBay. Depending on the specific category, the keys will be different. They can be visual things like the color. I'm not sure if you can see these down here, but this one has color yellow. They can also be non-visual things like interior material or country of manufacture. There are many ways that you could train a model to predict aspects. You can probably think of some. But there's a pretty glaring problem with aspects, which is something that I've suffered from many times, which is that they're terribly inaccurate. Users have identified that by lying about their aspects, they can pretty, well, not easily, but that is one way that they can try to push their search results higher up and do some search optimization. So aspects tend to be a pretty inaccurate measure of the qualities of an image. Okay, the next one is called manufacturer code. And this is sort of equivalent to product ID. So depending on the specific thing that you're looking at, they'll have some kind of manufacturer code which uniquely identifies, say, the type of shoe that's being sold. So if two users both decide to sell the same kind of Nike Air Jordan 1 high top whatever. They might append to that their MPN or manufacturer code, and then we would be able to tell whether or not they come from the same product. So then you could train a model that takes 2 images and determines whether or not they come from the same manufacturer code if you have that data. But that one is unsurprisingly low availability. That's for a couple of different reasons. First is that not every user wants to take the time to look up the MPN. It is a fairly long string of numbers and letters usually. Also, some things that we sell just don't have them, right? Like handcrafted goods aren't going to have a manufacturer code on them typically. Okay, so this leads us to the data type that we settled on, which is image title pairs. So every listing has a title listed right here, and every listing has at least 1 image. Most have, in fact, many images. I can't say that there's no data limitation in terms of the amount of image title pairs that we have access to, but it's pretty broad and covers every category. So that seems like a good starting point. So using this data, we could train a contrastively learned multimodal model. What is that? There we go. Okay, so as a refresher, whoops, I lost my track here. Yeah, so let's have a refresher on contrastive learning. I'll occasionally refer to these models as clip-like because I spend a lot of my time thinking about OpenAI's clip model. It's my favorite thing. So in order to train such a model, you need to have 2 separate embedding models. You need to have, in our case, an image encoder and separately a title encoder, often also called a text encoder, right? They have to map to the same fixed dimensional vector space. So in your mind, just pick a dimension and they're mapping to that space. So we calculate a loss function called matching loss as follows. You take in a batch of data and you feed in all of the images through the image encoder and all the titles through the title encoder. So that you have all of these large vectors. Now you can take pairwise dot products between all of those image encodings and title encodings, and you get this large n by n matrix. Cool. So then what we can do is we can calculate cross entropy along rows and along columns, add them all up, and then that is the loss function called matching loss. Just a small note there, in order to calculate cross entropy loss, you need to have a ground truth. And the ground truth for us comes from the main diagonal, which will be positive labels. So that makes sense because the main diagonal corresponds to the image title pairs that come from the exact same listing in your batch. And the off-diagonal entries correspond to image title pairs that come from different rows. So pretty reasonable. Okay, great. So minimizing the matching loss means that you'll push images and titles that come from the same listings closer together and images and titles that come from different listings farther apart. So pretty intuitively, that's a desirable quality. And then just as a note, you can separately use these, right? Because we have 1 image encoder here and 1 title encoder here. You don't need to always have a title. You can just encode simply the image, which is one of the nice qualities. So you can think of this as having like a title encoder and an image encoder that play together well and help train one another. Some helpful pictures to keep in mind, things that I've just thought were helpful over my months working with this kind of modeling. Since the embeddings are normalized, they exist on a sphere. That's item 1. And item 2, there are actually 2 manifolds here. So there's the one manifold, which comes from the title embeddings, and the other one, which comes from the image embeddings. And they exist on separate parts of the sphere. The fact that we're trying to push images and titles nearer to one another does not mean that these manifolds actually overlap. It is simply that the images and titles that came from the same listing are relatively close to one another. But you should imagine, like, here's North America, and that's where the image embeddings are, and then here's Africa, and that's where the title embeddings are, something like that. Okay, so that's the end of the review. Let's see the specific architecture that we used. So our image encoder is going to be a ResNet 50 model, and our title architecture is going to be BERT. But there's a catch. We load different initial weights from different sources for our separate training runs for the BERT model specifically. And both of these will be mapped to the same fixed n-dimensional space using some feed-forward networks. Yeah, so that's the outline of the architecture. Let's talk about some of that fine-tuning. So eBay has several internal models that are fine-tuned on our data. We'll consider two BERT-based models, which are trained on different, again, internal eBay data. So they're called English-based and multilingual. Pretty intuitive what exactly goes into those, roughly. Second. Yeah, so we'll use each of these as initial weights for training our clip-like model and carry out separate training runs. The selection of these weights matters, not because we care about the final performance of the BERT model that we fine-tune, but because they impact the training of the ResNet 50 half, right? Because that's what's going to be used in our image embedder. Okay, so additionally, we consider several different dimensions for our embedding space: 64, 96, 128, and 768. Generally speaking, if you're thinking about K and N, smaller means faster. But in our case, there's some acceleration and tricks that are done at index time. So it's not necessarily the case that we need super small embeddings in order to make this workable. Okay, so we trained many models, but for the purpose of displaying metrics, we'll consider just these 5. 4 of them are from the English-based BERT, and 1 of them is from the multilingual BERT, internal BERT variant, that is. Okay, so first, a word on data. So like I mentioned, the data is sourced from 2 categories: home decor and furniture. And we did actually train separate models for each of these, but in total, we used 8 million training image title pairs and 300,000 test image title pairs. One nice thing about using this type of data is it's plentiful at an e-commerce site, right? That's your bread and butter, our image title pairs. So as a side note, there are some complications when you're separating this kind of data into training and test sets. So you can imagine, if you will, that you have 2 rows and they have the same image, but they have separate titles. So, or distinct titles. So the typical move here is you would deduplicate your rows, separate into training and test, and then maybe undo the deduplication if you want. But in this case, if you were to deduplicate rows, you would have perhaps the same image in your training and your test set, but the rows would be distinct because you have a separate title appended. And this happens quite a lot because sellers like to, post the exact same listing, but say size 11 shoe or size 12 shoe, but then they have the exact same picture, right? Because the picture doesn't really matter. Also, there are kind of standard images that users will access to, populate their listing. So it's pretty common to have a lot of repetition, especially in the image section. Okay, so deduplication, the way that I just described, does not sufficiently separate images in particular. Okay, so the next kind of logical step that I took, at least when I was cleaning this data, was I deduplicated based on the image hash, and I deduplicated based on the title, which does work, but you've then thrown out a very large fraction of the data. Turns out there's, maybe not that many distinct images and that many distinct titles, at least compared to the 8 million that we get to start off with. Okay, so what I ended up doing to resolve this is I made a graph. So the idea was you treat every single row as a node in a graph, and then you put an edge between them if they either have the same title or if they have the same image. Okay, so that gets you some, nice graph structure, and you can consider the connected components of that graph. And then with probability, whatever you want, 0.9, say, you map each connected component into your training set, or probability 0.1, map it into your test set. So this doesn't get you a perfect split of the data. And there's some toying with that. In particular, if your components have very different sizes, then you might still have a fairly imbalanced data set. Not imbalanced in the precision sense, but imbalanced in terms of not being exactly at the 90-10 split you're looking for. Okay, let's see. So before we actually look at our results, let me just talk about the performance metrics that we used. So some of you will have probably heard of most of these. Perhaps they'll be new for others. So we broke them down. We used 4 metrics that we break down into 2 categories that we came up with. One is called descriptive metrics, and these are basically metrics that describe clip-like models. So so it's how well the image and title encodings play with one another. And on the other side, you have vision metrics, and these are supposed to be approximations of the downstream task of visual search. And we needed to have these before things could go into A/B tests just to make some claims that stuff was looking appropriate. Okay, so let's talk about the descriptive metrics. First is matching loss. We already talked about that. It's used to train the model. So the second one is image to title accuracy, which is pretty similar to the matching loss. It's, however, a little bit more intuitive, maybe more palatable. So imagine, if you will, you take a batch of data, you map through all the images, you map through all the titles. Now you take the first image embedding in there, and you do k nearest neighbors with k equals 1 among the among the title embeddings. So you get a nearest title embedding. Okay, so that title embedding either comes from the same listing as your image, or it doesn't come from the same listing as your image. So that's either a match or non-match. So it gets a score of 1 or 0. You can do that process for every single image embedding in your batch, and for many batches, you average all these values together. So that's the image to title accuracy. Okay, on the vision metric side, we have NDCG, which stands for normalized discounted cumulative gain. People just call it NDCG though. So this is a pretty typical metric in search. The idea is that you have a query that comes in, and that query gets some response of results returned, and each of those results either matches or does not match, and the results are also sorted. So NDCG rewards the set of results for having relevant results higher to the top, okay? So it, in particular, really cares about having things in the first few places. So just a couple of comments there. This is the formula DCG, which is the unnormalized version of normalized discounted cumulative gain. You can perhaps imagine what the normalized formula looks like, or you can look it up. Oh yeah, and then in context for what this means, when it comes to the visual search. So an image embedding is submitted, and some images are returned as results. Great. So then what we care about is the matching or non-matching between those images and the initial image that was used as a query. So we need to have some definition of what matching is, which is, something that we had to discuss extensively. But the thing that we use for the purpose of these metrics here is just whether or not they belong to the same category. I had shown you those sort of descriptive categories earlier, things like dining sets and men's athletic shoes, that type of thing. Okay, so that's NDCG. Next is mean average precision, something probably most of you have heard of. So I won't get into the formulation there, but I like to think about it as an order agnostic version of the DCG. So it doesn't care so much that your results are at the very top, as long as they're in the top K. Okay, so here are the results of training our clip-like model using the different BERT models as starting weights. I don't report the actual numbers, just percentage scores relative to the leftmost model over here. So as a reminder, while the columns are indexed by BERT models, the results actually describe the performances of the corresponding ResNet 50 models that were trained. A little bit of wiggle room in there for the image to title. Okay, so yeah, the bold scores are the best performers. I can't actually show internal performance values, which is why everything is scaled relative to the BERT English 768 model. But you can see some trends here. You see a generally degrading performance as you go to smaller dimension, very intuitive. And you also see that the multilingual model lends itself to better overall performance. So obviously we can't conclude anything general from this or the other experiments we did, but it does suggest that initializing with weights from better text encoders can lead to better trained models overall. Better trained vision components overall. So, okay, now we've got the pictures. So let's see some examples. So here we have some clocks. You can see the search query above. These are the search queries. And then you can see the results in the columns below. I guess it's a little fuzzy for you guys, but this first one, it has golf balls. It's ringed by golf balls. And all the results are ringed by various like sporting balls, like there's pool balls and footballs and that sort of thing. The next two clocks are metal and wood. The results are also metal and wood. And the last one's got some kind of retro feel and some text, and the results look like that too. Okay, let's look at one more set. These all come from our beta version, which was deployed to a fraction of users some months ago. Okay, so here we have so pillows. I won't go through them. You can see some similarity. I'll just talk about the third one. So it's kind of funny. It's got this like dog face printed on there. The results also all have dog faces. So the first thing that you learn when you work at eBay is people have terrible taste, and like these are just everywhere. But I think this is actually kind of an instructive example. So if you go to eBay and you type in dog pillow, you don't get this for the most part. You actually get pillows for dogs to sleep on, though you will occasionally come across an example like this. So a quick way to filter out those examples that are those results, which are pillows that dogs sleep on, is to find one of these and click See Visually Similar Items. Okay, so we've talked about our eBay product, but now I want to talk about one of the findings from this work that has broader implications, maybe some academic relevance. So let's think back to our first NLP class. So you learned that the glove word embeddings allowed for this kind of linear analogy property. So the most famous one is you take king, you let's see, subtract from it the embedding for man, add for it the embedding for woman, and then you get a queen, or some approximation of queen. So a couple of observations. The first is that we saw a similar property in our title encoder. Okay, not perhaps super shocking. And the second observation, so recall that clip and clip-like models embed both titles and images into the same vector space. So this allows for a question: can we replace some of the terms here with images? And the answer is yes, we can. So to see what that would look like, you can imagine something kind of like this, where you replace some of the terms with images, and you can still maintain the analogy diagram to some extent. So this is actually related to a pretty popular model right now, something everyone's been talking about at this conference. So for those who aren't familiar, DALL-E 2 is the smash hit model that allows you to enter some text and get out a often photorealistic, or at least very convincing, image of whatever your text describes. So it is in fact trained using OpenAI's CLIP model, the CLIP embeddings specifically. So there are a couple, very interesting components to how they trained everything, but there are just a few relevant notes here. First is that image embeddings are passed to a decoder network in order to produce these images. So they take an image embedding, decode them to get the image. And moreover, text is actually mapped directly to image embeddings using an encoder network that attempts to approximate image embeddings from text, which is kind of a weird move that they do talk about in the paper. So in addition to generating images from specific text encodings, you could also take two text encodings, walk between them, and generate images from all of those. And that's what they did here. So they took the embedding for a photo of a Victorian house and the embedding for a photo of a modern house. So rather, they took that text, embedded each of them to get image embeddings, decoded each of them to get these images, and then to walk between these images, they simply took steps along a straight line between those two. Except it's not actually a straight line because everything's on a sphere, so it's a cylindrical line, right? It's on the surface of a sphere. It's a great arc. And so along the way, they would decode each of these to produce these cool images. So they describe this as a way to explore clip latent space, which I think is a pretty cool idea. So we have another, albeit much more limited, way that we can explore embedding space, and that's by using the scheme described in the previous slide. So for this example, I took, whoops, didn't change it here. So for this example, I took an image of a red chair, took the words red and blue, embedded them, and then did the appropriate arithmetic relationship to get this embedding out. So if I was working at OpenAI, I would just take this embedding and decode it to get some kind of constructed image, but I don't work there. I don't have the capability to decode that. So instead what I can do is I can look over a fixed data set and I can do k-nearest neighbors. And this gets me, perhaps an approximation of looking through embedding space. So in this case, when I do this adjustment, I can actually find an image of a blue chair, which is pretty cool. So there are a couple of caveats here for this and the one other example I'll show. So the variances of the image encodings and text encodings are not the same. So there's some scaling and normalization involved. Images also have many qualities, so changing, just using one term might not do exactly what you want it to. But with this, you don't just have to do word embeddings, right? You can do title embeddings for this, so you can use multiple words. And this changes the structure instead of some more simple quality of the image. Yeah, so based on this, I do foresee rich use of these image title embeddings in e-commerce applications in the future. Cool. So I'm going to end it with that. Thanks, everyone, for your time.
We have questions.
Hey.
Thanks for the talk. Did you also look at how vanilla clip works on your data set?
Yeah. So we didn't look at it on our data set for a number of reasons, but it was used for a related challenge that we had as an internal hackathon, and this style of modeling using the BERT architecture did outperform Clip on that. Yeah, great question though. I expected that to be the first question.
You use pre-trained image of pre-trained representations for the resident, some ways.
Yes.
And does the contrastive PO or simpler type of pre-training help there, or your images are enough to pre-train?
Oh, maybe I'm sorry. Maybe I didn't understand your question.
Yeah. So you in your multimodal model, you have a resident, right? Mm-hmm. And initialize it from some contrastive pre-trained model.
Oh, for the ResNet? No, we actually initialize using vanilla ResNet.
I see. You think that these 8 million images are enough?
Well, it was enough to get an improvement, like we could measure, but I think it is probably the case that using something pre-trained would have been better. That's a good point. Yeah.
The picture versus text. So what is more important? What do you think?
I think text is more descriptive and it's easier for us to communicate, but it's also limited in that it is very easy to lie with your text, and that's sort of the problem that we're trying to counteract. Yeah. Oh, I'm sorry. He was playing some less.
You worry about users adversarially engineering their prompts when they post the titles of their images, their products.
I see. I suppose that could be a concern if they're trying to affect the performance of the model on images that look like the image that they've appended to their prompt. Yeah, that is a concern going forward. That's a good point.
Could you explain a little bit more about your intuition about the various manifolds of the image embeddings and text embeddings? Have you visualized that, or have you trained a classifier which was pretty successful?
Well, actually, the way I observed this was through seeing some results that I found confusing. So I had trained one of these models, and then I was looking at the R-squared distance between images and between an image and its corresponding title embedding, and it was 200 or something. It was, or wait, that can't be right because it's normalized, right? Anyway, point is that it was bigger than 1, and that was confusing. And the point is that an image embedding is a worse approximation of its corresponding image embedding than just an average image embedding is of itself, because they exist in separate pools.
So this is it's hard to imagine because it's high dimensional, right? So it's this high dimensionality issue. Okay.
And maybe last question.
Do you do search on the embeddings on the embedding space, or do you directly do KNN, or do you have to sort of transform them? And does the way that you store and query those vectors matter? Are these interchangeable? The way you call them, the database part?
Okay, so if I understand your question, so the first part is yes, for the purposes of what I described here, we just do a KNN search. Insofar as storage goes, there are a number of optimizations and tricks. If you've heard of PQ encodings, that's the technique that we were using to speed it up, as well as some what do you call them? I can't remember the term, but doing some neighborhoods so you limit your recall. Yeah.
Okay,
Thank you.